question for all of our parts. Each team will have a total of 12 minutes for the presentation, followed by a 5-minute question and answer session will be done. The buzzer sound will sound at the 10-minute mark as a heads up, and the 10 and 12 minutes to signal that it's time to wrap. Please note that exceeding the time limit will result in a penalty to your current scores, so do keep an eye on it. Participants will be judged across 5 criteria: the depth and accuracy of the content and understanding, the clarity and interpretation of the results of the ideas, the quality of the presentation and communication, the effectiveness of the visual aids and overall organization, and finally, the performance in the Q&A round. The decision of the judges will be final, and the results will be declared in papers. And a quick note for our audience: if time permits, the floor will be open to your questions after judges have had their turn. So we request that you hold your questions until then and do not interject between the presentation. We also request everyone to please put your phones on silent in relation to the presentations. We will now begin with the presentations. I'd like to call Anushri Srivastava from St. Stephen's College to present on the topic estimating GNSS performance in extreme space weather conditions.
Good afternoon, everybody. I'm Anushri from St. Stephen's College, and I will be presenting for the estimating GNSS performance to the extreme space weather conditions. So I've divided the topic into 3 objectives. First, we go through how does the signal transmission works, and then secondly, what are the unexpected effects on the GNSS signal and subsequently the position level, and thirdly, the impact of geomagnetic storms on the position of the satellites. So the flow will be as follows: and briefing about the different concepts that I will be using, then the methods and the 4 principles, which is the weighted analysis that are used throughout the topic. And to support that, I will present some results from a case study that was over. So, GNSS, Global Navigation Satellite System, it refers to a constellation of satellites which translate positions. So, there are hundreds of satellites which orbit Earth. And how do we communicate through the satellite? So, precisely, we have the PNT information. PNT information stands for the positioning, navigation, and timing information. So, there are satellites. So a satellite sends us a signal, and on Earth, we receive them. So from that, we can actually calculate the position because they are radio signals. So we know their speed. They travel through speed of light. If we know the time difference between when the signal was emitted and when it is received, we can actually multiply it to get the distance. But the catch is that Earth is surrounded by an envelope of atmosphere. There are different layers, and it is not pulping, so the signal undergoes reflection and refraction. And one of the things that is of prime concern in this project is ionosphere. So ionosphere contains charged particles. So when the signal comes, it's a radio signal. So it interacts with these ionosphere particles in the ionosphere, and the signal gets reflected. And when the signal gets refracted, so the calculated distance, which we calculate from the time difference and the speed of light, is actually shorter than the distance that we actually observe. And then geomagnetic storm. So what is geomagnetic storm? Geomagnetic storm is a sudden outburst of solar winds, high pressure winds which enable charged particles to travel through high speeds. So these charged particles, when they travel through high speeds, they compress the magnetosphere of the Earth and very significantly interact with the particles in the ionosphere, which disturbs the path of the signal from the satellite we have seen. So to summarize, the satellites in space transmit signals which are affected by the ionosphere as they reach the Earth. Then the GPS receivers calculate them, but the signal is reflected due to TEC. TEC stands for total electronic content. I will use this term a lot in my talk. Yes. And then this results in delayed arrival. So essentially, the aim of the project is to estimate the position error due to the ionospheric delay, and what can be a remedy to them. So I have been talking about the speed of light and the signal at that time. So to quantify those things, I want to introduce 2 parameters, simulate and calibration. So these are the parameters of Phoenix data. I've been talking about the information which we receive from the satellite. So that data is in the form of Phoenix data. Phoenix stands for receiver independent exchange. So two parameters of that data is pseudo range and carrier space. So as I said that the data is in radio signal, so it has space. So we can actually get the because we have precisely have the information of the satellite and its position. So we have the data by the time when the signal was emitted and in the phase that we received. So that is the carrier phase, and pseudo range is the distance which we calculate. This is a calculated quantity because we know the time and we know the speed of light, so you can calculate. But this pseudo range is said pseudo because, as I said, it is not the true range. It is due to it has the error due to time space. Okay. So what we are very familiar is with GPS. GPS is positioning of moving objects. But let's get to the basics to get the position of a static object. So precisely, evaluation of the station position, station which has the receiver themselves. So there is a software, article software made by a physicist in Japan. So through the software, we can actually translate that Unix data into visible things. So in the graph towards your right, you can see the coordinates east, west, north, south, and up, down. So these are basically the three coordinates of the. So we can see that there is a zero line, and the zero line defines the actual position. When we set up a station, we actually know the actual coordinates of the station. So that represents the zero line, and then there is this the fluctuation in error throughout the time. So the x-axis represents the time, and this scatter plot towards this. All these red dots are the station positions evaluated at a time period of 30 seconds. So the Linux data that we receive from satellite or the data that I use, it is timestamped for any 30 seconds. So this is a scatter plot. If there was no ISP delay or if there was no variation throughout the day, this would have been a single dot. But it is not, and so this is the position error that I am talking about. I mentioned I mentioned about geomagnetic storms. So how do these position errors are different from a qualitative to a storm? So this is a four window. So this is from the data of 10th May 2024, which is the case study that I'll be presenting later. So this is a glimpse of the data there. So this is 4 days. So 9th May, 10th May, 11th May, and 12th May. So the storm had hit Earth on 10th May. So we can essentially see that there is a position peak that we receive on 10th May when the storm has hit. So this establishes the correlation that when the storm has hit, the position error has increased. So we can say that a storm has impact on the signal delay and subsequently on the positioning. Wavelet analysis. This is one of the core principles or the core techniques that are used throughout the project. So wavelet analysis is a time frequency plot simultaneously. It is different from Fourier transform because Fourier transform you either have a time plot or you have a frequency plot. But through wavelet analysis, it is like a color map. You can I show it. You can represent it through a color map where you can see time and frequency both. You can actually observe those fluctuations. Like there is an increase in tech throughout the day due to diurnal variations when we are facing the sun around the noon time. But how do we distinguish that it is due to the storm? That is when the tech fluctuates a lot because there is a sudden compression of the magnetosphere and magnetic effects. So wave analysis is a unique technique because it has not been yet used by people to work on this. People have used wave analysis to do gradient of sea temperature, but not positioning it. So I've done used wave analysis to do this. So first inference is that the maximum power represents the maximum position error. So the intensity of the position error, the extent to which there is position error, that is measured by the power in the wavelength power spectrum. So we can see that there is a one-to-one correspondence. The time at which we observe the maximum power correspond to the maximum position error. So through this, we can say that we can actually use data analysis to use it here. Secondly, now I move towards presenting the results of the case study that I've worked on. So I would like to introduce one term DST. DST stands for Disturbance Storm Time Index. It basically is a measure, it's a way to quantify how impactful was the storm. So it is in nanodecimal and this is negative the DST goes as negative because it decides that how compressed is the magnetic sphere of a so that is the DST. And the negative, the DST index is the more powerful the storm is.
So this is for two stations that have taken the impact of the storm in positioning error of two stations, IIT Kanpur and Lucknow. So we can see like when the DSP was minimum means the storm had impacted towards police. We observe the maximum position error in both the stations. So there's a comparison for two stations to verify that the position error is consistent with all the stations and it's not a systematic error. So this is that. And yeah, rated power spectrum. So this is position error plot, and if we do it through wavelet analysis also, we see that we get very close results. The time of maximum power that we get is 10.81 hours, and the time of peak from the roti plot. So roti is rate of tech index. So as I said, that we are looking for fluctuations in the tech. So it corresponds to roti. So we can say that the wavelet analysis is actually powerful, and we can estimate the fluctuations in the tech through the wavelet powers. So to conclude, I would like to say that GNS is highly sensitive to ionospheric disturbances, and it is important to account for these disturbances because if we look at its application of positioning in aviation or navigation, there precise calculations are needed so that because we can say like the position error of like 5 meter, 6 meter doesn't matter, but it significantly matters when you talk about its applications in defense or aviation or navigation. So that's it. And the further work is to actually do it for moving objects and also how can wavelet fence building to build a model to wavelet power spectrum to account for the things. I've done this presentation is a part of a project that I did this summer from the Indian Academy of Sciences under Professor Abhijit Ratna. We now begin with the Q&A. Jarvis, please move the Q&A round. Also, 5 minutes may clear buzzer sound is inside. I think that going to get on the wavelet analysis. Yes. So out of the wavelet analysis, like we observe a position spectrum, but as you can see, like we can observe peaks like on all days because of the diagonal relation, because we relate position error to 10, the total electron content. So every like around noon time we are facing the sun. So there is a variation and like due to that diagonal variation only, people see a peak in 10 every day. But how do we distinguish that this is not a pointing but a storm has hit? Because that we cannot distinguish from that. So we talk about the fluctuations in the tech because if the storm has hit, then the ionic particles in the ionosphere they will undergo changes or will rapidly fluctuate. Why do we want to just getting paid in the storm? Because information about the storm is irrelevant. But we cannot translate it into this thing. I am trying to. This is like a. This is given like we know that there is a storm because it is a case study on previous before. But if we do not know, then how can we basically to relate the rate of text index to distinguish it from a nominal text, a peak to a strong text peak. That's why we use wavelength because here we do not see multiple peaks. This is also a model, but we do not see multiple peaks. We see just one because the rate of text was massive. So you want to find signature of instead of rest. The critical period when the tech was fluctuating. So it's you will statement is the magnetic field reading. I feel like it's the negative correlation. No, sir. We actually there is an analogous to DSP index, which is KP index. So DSP index itself measured to be negative because we measure it in the correspondence to all magnetic fields. So when a geomagnetic storm gets the sign, yeah, important of the magnetic field. So it's the way to quantify. So the magnitude is important. The more negative the DSP index is, it means the higher the storm has been. I have done various case studies for DSP index. Like here the DSP index is very. DSP index can it be positive also? I think. Or it's by definition positive. It is negative because when the geomagnetic storm hits, it compresses the magnitude. Actually, the DSP index measures the decrease in the Earth's magnetic field.
So since it measures a decrease, I think by definition it is
because it be cancellation of the fields, enhancement of the field,
Yeah,
based
yeah.
on what the solar wind wrong.
right. So it always measures the way it has been defined is that it is used to measure how much the field decreases. What's magnetic field decreases in presence of storm.
Is the change.
Yes. That's why it's known.
That. What's is looking from inside the earth? How is that affected by sewage?
So the magnetic field, which is there around the earth, where the storm gives, so it has high speed charged particles which impact the earth.
So it's the Earth's view.
It compresses because the charged particle interacts with the magnetic field of the earth. That's it gets it interacts with the field and there's the phenomenon of magnetic connection that takes place. So the magnetic because of the interaction of charged particles and the magnetic field.
Accidentally charged particles to the part of the
It is because due to that interaction only. And like they travel through the magnetic field lines of the earth through the poles and that's where all of the formation is. It is because of the interaction of the high speed charge particles with the magnetic field.
Or the field that they charge particles are not an observation. They also carry magnetic field. Internet system. So which would then interact in addition to the interaction of the charge particles in the presence of magnetic field.
The magnetic field created by the moving charge particles. So current.
Thank you, Vanshri. I'd now like to call Sandeepan from Tribunal College to present on the topic enhancing trans transgender performance with labels for space-based associations.
First case design. Work started with three in the world where we now important compact and efficient and cost effective techniques. And to design something which is also lightweight and compatible with the upcoming technologies and can be taken survive the mass conditions based backgrounds and also preferences. Which led us to explore microchip patches. These are cleaner low profile materials which are currently being used in modern wireless systems. One of the major advantages of this idea is that it's easy to fabricate and they are compatible with the modern display technologies. And depending on their use cases, you can adjust the material and make it more security on the requirements. Currently, for patch antennas, the major issues which we face is it has low gain and comparatively lower bandwidth. But if we play around with the substrate rate, we can enhance its performance, increase the bandwidth, and also increase the speed. Majorly, a patch antenna has three major components: a ground, the patch, and the beneficiation. So when we excite the patch, it creates surface space, which then radiates into the free space. For the substrate, we majorly use FR4 as a substance, and the ground and the patch are usually of the same. So how does the engine excitation goes? In our case, there are five major ways in which we can do it. So either we do it using a microstrip line. If we look at the patch regime here, where this this part of the area, which is being connected to the field end, it is directly there and there are no slits present there. That is the case where we directly connect the field line to the patch and the process is what we call as microstrip field line. For our work, we used insert field because the impedance of free space is 377 ohms and our antenna was working at 50 ohms. So we have to match the impedance. Apart from that, another technique which is commonly used is coaxial profile, where you connect the patch to the ground using a coaxial wire. Apart from that, there are two also major techniques which are called aperture coupled field or proximity coupled field. These two are comparatively tougher to fabricate, and which is one of the major reasons they are very much common needs. So proximity coupled field, we've seen the best results which work in the patch. So let's say we have a patch antenna. How do we verify that what we are targeting to do is correct? So the first step is to make a 3D model of the antenna and to simulate it in answer saturations or any use of detecting the block. For our case, we plotted the S11 block and our target frequency was around 6 gigahertz and we see a sharp dip around 6 gigahertz in our S11 block. The gain block shows a good direction. So, apart from that, we also plotted the O and cross polarization and VS of O. For co-polarization is basically the polarization at which an antenna speed. So that is what we want. Cross is something which will contribute to the numbers. In our case, the co-polarization was higher than that of the cross polarization, which is desired. That means an antenna is more tuned to the actual frequency data which we want, not to the noise. And for the base approach clock, it is coming to around one when it's reaching our target frequency. That shows that the antenna had an ideal match. Now, patch antennas are highly sensitive, and you can't put them in very harsh environments. It will get easily destroyed. So, one of the techniques which we are using for to protect the patch antenna is using redomes. Redomes typically are used for dynamically cooled antennas, where you have to place a redom so that it doesn't get affected by the outer environmental conditions. Red dome is basically short for radar dome. Now, one of the tasks that we are using red dome is to minimize the degradation which is happening when you place a red dome without any. And I want you to, one of the reasons why degradation is highlighted here is because this. So this was the very first item which we like to simulate, the antenna and the red dome. And technically, if you just take this and use it in the physical world, it won't work. One of the simplest reasons is because if you notice that the patch and the redome has a gap, there is no support structure. The gravity will act and the redome will come crashing into it. But luckily for us, ANSYS doesn't account for gravity. So our game simulations work perfectly. But then it showed one that the game with the redome was higher than the game without it. That's not theoretically possible. If you're placing a redome, you're supposed to see that the gain is supposed to reduce. But our simulation said that yeah, if you place a redome, you're going to get a bigger gain. Now, one of the reasons why this happened is because it didn't have any covering structure when we first simulated it, which we actually later improved. I'm not sure if it is visible. for the- so in the actual diagram, there is a layer here, which is like slightly shaded. Can you tell me the approach? Diagram is probably using this. Yeah, it's, I'm not sure how well it will be listen to this. But if you look, there is a structure here, which is placed, which we have added, which we did a finding of these simulations. And that simulation showed what the theory showed that yeah, when you place the ladder, your game is supposed to decrease. So the mistake which we did here was we didn't account for the radiation signals coming from the side. In analysis, when we are simulating it, the radiation loss is compared to today bigger than water antenna is. So those which are coming normal in the antenna will be affected by the radio. Those coming from the side were different, which actually increase the peak. When we covered it, we technically made all the radio signals coming to actually face the radar, which majorly decrease the peak. And this is what theory also states that whenever you place an radar, it's supposed to get a location. Now, one of the few errors which we face when we are placing the radar is not all of your radio waves will be normal to the antenna. Some of them will be coming from the side, and that will be traveling larger distances than those hitting normal. So let's say a wave is coming from this side, and if there is a radar ball which is this side, it will face, it will have to travel more in the radar than actually in comparison to those hitting normally. Because they just have to pass through the radar thickness. So that error can be reduced if we use something like variable thickness reduce. But then the challenge of application of such reduce increases. Now, one of the things which we will be trying to do is to see if patch antennas and the radon structure combine both for CubeSats. Traditionally, CubeSats use the dipole antenna configurations. So it is one of our tasks to see those both. And the future also involve simulating dipole configuration and seeing if patches provide better performance or it's dipole. Then you simulate patch antenna array and see if it can be used for radio storage configurations and we design the number of patches for the whole antenna configuration. So these are some of the differences which we use for relations.
Now we can
So what is the we use the TML, TMA. The material is called the material is called polymer. Polymer? Polymer? It's a polymer. Polymer. Yeah. The direct question was that what losses in mind. Oh, that in a way, right? We expected. Yeah, so there is a distinction made on saying pain is reused or replaced, and the signal is reused or replaced. We can run it through simple problem of normalization. Okay, in the definition of the change rate of gain, basically the integral profile. Okay, in the process, you might misinterpret. Okay, now there some ranking suddenly change that area. Okay, which we also pointed out that it's one-sided affecting one's line is too hard, right? So we might initial conclusion may be simply affected by it may have a reduction in the signal coming from the top. Physical reduction. Okay, but interpreted as the gain and experience because of continuous. That might be what.
What are the valuations that we need to cognitive development pieces of the
The patch engineer dimensions was so the width was around 40 millimeters. The Kelvin one was around 10.3 millimeters. And the substitute height was so at 62.
And the success of the parent does not play a role.
The thickness of the patch is I don't exactly remember its value. Yes.
How did you incorporate that radar for simulation? Parameters. How did you incorporate radar in the simulation?
So we just like we did this is we took the patch and came as it got
In the simulation, simulation.
yeah, so we in the software we designed this radar and we just placed it
What parameters, what physical parameters? factorize the way of because of some boundary connections and the way you see the patient.
It's really just using the right images. What are the distance? The distance between the patch and the kilometers of effects. Frame price. What? So we actually also run a parametric suite, which was did optimal distance. Basically, when we basically set these up at certain distance, we wanted to have the internal reflections which is happening inside of the rhythm. We want to construct it so as to not doing the income. So where each other effect is doing. So what I mean is here the radiation is coming from the top. Yeah, the radiation is coming from the top. Some of the waves will enter because it is a changing medium, so the impedance is not properly matched. So this is a different medium, here is a different medium. So when the signal comes, some of it gets transmitted inside, some of it gets reflected. Then when it is also passing from here to here, some of it will also get transmitted, some of it will be different. Now this reflectivity go back here. And from here, some of it will try to get out, and some of it will again get out. Now, the wave which is getting out, it will interfere with the one which is coming inside. And that, if destructive interferes, will lose the signals. You don't want it. So you want it to construct the limiter. So you just do the general permission for constructing it, then you can figure out it. And then you basically see like run a parametric suite, certain distances are covered as a and see which is typical of distance. So all your simulations assume that we're studying the radiation patterns. Yes, right? So suppose you want to use this approach, assume that the receiving of this. Very important. Huh? That that's what is reciprocity. So you like to study of radiation the same as how you behave. Right.
And then comes back. Yeah, I'm supporting and feel more time the week. So the week is basically time this. But anytime I'm free, it is a vein, it's just basically different. So it exhibits two types of motion. One is translational and one is alienated aspect. So we model the translational aspect and we've been talking really about the rotational aspect. So I would like to talk about how units works. So the angle of the tag refers to the angle between the velocity vector, the direction of motion of the body, and the surface of the So if I'm throwing like this, then this is the velocity and this is the so this is the angle of tag. And the angle of launch we're taking as when we reach over 50, it would be slightly angle of vector. So there are also second philosophy and this is the angle of tag. So I would like to talk about the various steps. So if we write down the various in the second law of the system, we have three major processes that are as law of the
So one is the air trap that is opposing the velocity. The obvious one is gravity, that is downwards, and then there's also an aerodynamic effect, which is acting perpendicular to gravity, so it's lifting it up. So to find the expression for the air trap, it will be that as number, which is given by rho b equal to then what is the density of air? Meaning the velocity of 50 derivative of air, and the diameter of 50 equals to viscosity. So we calculated using the average values and we got that number as this. And this gives us the form of the back force as this. And there's simply the coefficient of drag, which is given by this relationship, and it is a quadratic expression of the angle. So let's look at the lift force. So the lift force actually like a controversial topic. There are two major arguments that are put against each other as to how the lift force works. So one is based on the Newton's third law. So that since the airfoil exerts a force on the air molecules when it moves, the air molecules exert a force back and hence it distributes. And the other argument is based on gravity. So even in this, there is one widely popularized incorrect theory, which is called the equal transient time theory, which says that uh, the pressure difference is created by the air traveling faster on top because the upper surface is curved. So the air has to travel faster in order to meet the air flowing at the bottom at the other end. But this is actually not true. It is misconception. What really happens is that when the frisbee moves, there's high pressure that is created in this region, like it's the red part. So that is the region of high pressure that is created. And then behind it, it's as if the thing has moved out of the thing. So there is a low pressure region over here. So what happens is the air accelerates and it rushes from the high pressure to low pressure. So this high velocity of the air creates a region of low pressure on top of the thing, and then at the bottom there is no such pressure resistance, so the air is not accelerated. So this is a region of high pressure. This is according to Bernoulli's principle, and this is what creates a pressure difference on top between the top and the bottom surface of the city, and that is why it is created. Now, the Newton's third law and the Bernoulli's argument, they aren't actually separate. One is based on conservation of energy and one is based on conservation of momentum. So both of them can be used to calculate the lift force. And here we use the Bernoulli's principle and that gives us the form of lift length as this. Where CL is the lift coefficient and it is a linear function of the angle. Now I'll be talking why about the various aspects of the cookie. So uh, so when the 50 moves, we know that the air has a lot of different speeds at different points around the cookies. So there's different pressure at different points. So we take this point where the center of pressure, which is the average deviation of the pressure. And what happens is, as the angle of attack changes, the pressure at every point of the flipping will change. So automatically the center of pressure also changes, and it gets shifted everything away from the center of gravity, which is in front of the flipping. So that is now the center of pressure is also the point where it indicates that the lift force or the aerodynamic force is acting, just like at the center of mass, we say that the dapple acting is center of mass. So since the center of pressure is shifted ahead of the center of gravity, there is an axis acting here. There will be a torque about the center of mass due to this aerodynamic force acting on the center of pressure. So what happens is if we were to throw the only a piece of paper and it was not spinning, then the torque would actually flip it over and would not fly it out, just fall down. So that would also what would happen in the 50
if it were not created like a gyroscope. Now, gyroscope has two properties. It has gyroscopic inertia and gyroscopic precession. Since the axis of gyroscope when given a high spin and has high angular momentum. So, so gyroscopic inertia is basically the property of the gyroscope to remain spinning, uh, and the high spin gives it stability, so it will not stop spinning unless some external forces apply to it. But even when an external force is applied to it, what a gyroscope does is it copes with the external force by precession so that the gyroscope does not lose stability and it still keeps spinning. So this is what happens to the flipping. Um, so if suppose the flipping was spinning clockwise, then using the pen and move the angle control point downwards and then the torque would point towards the right. Here, this if left is upward, then the process it is using torque towards the right. So what the angular momentum vector tries to do is it tries to move towards here. This is called telescopic precession. But what happens is since the split is spinning, instead of sticking directly towards the torque, it gets swept sideways. So we say that the spin axis precesses. Um, so this creates a wobble in the frisbee, but it does not stop it spinning because the higher the spin is, the slower is the precession. So it's inversely proportional, and this even if I throw it, we can see that it's slightly wobbling like that, but it's not really falling unless the wobble overpowers the precession. Now,
I think the question motion now. So first of all, we have the drag, which acts opposite to the velocity direction, so it acts in all three directions. All those analytical forms that you can have, in the x direction, it's negative rho CD A V times Bx upon 2. And similarly, Swift only acts in the upward direction, which is z, and it is also proportional to the square of the net velocity, where its expression is given by rho CL dv square by 2. The next step is to use the Newton's third law and the mode that we are familiar mdv by dt equation. So while using it, we obtain three coupled first order differential equations in all three directions, x, y, and z. And their analytical form that we can have. All right. So now we'll be setting the constants. It's hidden below the title. The analytical form of CL is given as CL0 plus CL alpha times alpha. CL alpha is basically the coefficient of the left force, which is dependent on the angle of attack. Alpha is taken as the angle of attack. So G will take the 9.81, which is the standard value. Mass, density, and area are standard values of their respective components. CL0 is basically the lift force which is produced when the angle of attack is 0 degrees. CL alpha is the constant, this is dependent on alpha. CD0 is the minimum possible drag force which is produced at some angle alpha 0. Because CD is equal to CD is equal to CD alpha, alpha minus alpha 0 whole square. So at alpha is equal to alpha 0, we obtain our minimum drag, which is CD0. Usually we're going to through the velocity with V1 is equal to 40 feet per second, which is the average throw of frisbee. We're going to take the long side and not as 1 meters, and we're going to start increasing alpha in steps of 0.1 degree starting from 0 to obtain the optimum condition. So this is basically our relation between alpha and range. So basically, if you can see, range first of all increases when we increase alpha. It reaches an optimum point and then starts to decrease as we decrease angle of attack at some particular theta, which is the angle of launch. This is the general relation between max range and the launch angle. And then this right here, the relationship between launch angle and optimal alpha is the relationship. Like optimal alpha is the angle of attack at a particular theta, at which we get it the max range. This is the general relationship between alpha and height. So as you can see, at angle of attack 0 degrees, for initial 5 degrees, we do not retain any lift force. So hence the height obtained by the frisbee is the same. Then as we start to increase alpha, we reach an optimum point of 1.73 meters of height at alpha equals to around 24 degrees. This is again another simulation of launch angle versus max height. This is a 3D trajectory that we plotted. At theta equals to 33 degree gives us the overall max range which we can obtain at particular value theta and alpha. And this is the max height trajectory theta equal to 90, which we do expect.
So now we on a one.
You are taking drag only in the velocity direction. It's also spinning. And does that also add to some kind of, anything that spins and it's just really, but it's to the spin itself and the drag.
Yeah, so this was a concept which we studied was the Magnus effect, which basically pushes the frisbee to into the third dimension. But as we were studying its analytical form read something as S omega cross V. The S depending on the interaction of the frisbee with the environment, and it was apparently only 0.01 times the drag and the lift force. So we neglected it over here, but then in the real life, when we launch the frisbee, it obviously isn't going to be straight. It's going to be tilted, and the tilt will hence induce the Magnus effect, which will turn the frisbee into the third dimension.
And in your simulations, what kind of spinning break?
In only what the translation dimension.
So that's a very good question. How does the translation speed compared with the tangential speed required by the spin at the Asia just to get a gauge for the ability.
We just thought of it as the angular velocity between 1 hour, which we used again. We just take, you're asking for the angular velocity, right?
Yeah, so that is a angular velocity. There will be a tangential velocity, right? The two edges. This was right? This is going backwards. This is going forward. How does that velocity, the relation to physically, compared with the transport velocity? Is to see the relative importance of spin and
We
in whatever simulations we've done, what are those critical values?
we just the launch velocity can be 20, and the bound for the inlet velocity.
We have some angular velocity, right?
Yeah.
Huh?
I said that it's very high, so that it's so high that it accounts for the stability. But we didn't really look into how that velocity compares with the transition.
Yeah, so you take that and take the radius of the frisbee.
Yeah.
And calculate the number, which is the tangential.
Just using
I was just curious because square roots.
just using the equation we have.
Right. Correct.
Have to consider the slowing down of the distance. Yeah, there are any kind of also.
Yes, as I think you get from you to think that all you simulation.
It's not
Yeah, that's we can stay on that cell. We can stay when we let go of it.
But they have some spins
I don't
resulting from
really since it's spinning, how is it helping the spinning fly? But we didn't talk about the mathematical aspect, like math equations.
We have to consider the air channel.
This and that.
We know not have easy problem. Because since it is story, especially on
So one is economic management. They are the highly sensitive market business, which is important and interaction between base and transparency. It's been these main such by a sensitive market because they are fixing applications, environmental systems, industries and defense and global technical. Plus, our information to work on this. So I'm using medium paper cell based it uses NMR technique, non-linear mathematical configuration, and we were able to achieve a sensitivity of 10 picoresca with a bandwidth of 24 kilometers. Working principles. So, the set of this, we have a medium paper cell with a magnetic field and by linearly polarized light is passed through it in optical counter radio patterns. And then we create an atomic alignment. This atomic alignment is about the magnetic field. When it cross the gamma frequency, it creates circular birefringence in the medium. Due to the circular birefringence, the polarization of the laser light it rotates, and this rotation is directly proportional to the magnetic field. Now, measuring this rotation using balanced polarity, we are measuring the magnetic optical pumping. Optical pumping is basically creating the population difference in the Siemens sound levels and the ground state. It occurs with this the two components of laser polarized laser that is sigma positive and sigma negative. They have different selection rules. So we have a symmetric accumulation of atoms in plus minus ng states, and this creates what we are calling as atomic alignment. This atomic alignment is in XY plane, and it discusses about the magnetic field which is in Z axis, and this magnetic this precision is okay, so at this point there are three things that is happening: optical pumping, precision, and spin relaxation. When these three effects come at steady state, the atomic alignment is at a steady angle theta from Z axis. This theta is given by this formula. Now, because of this thing, this circular birefringence is induced in the medium. This circular birefringence rotates the polarization, and the rotation is given by this formula. We see that the practice mix of the atomic mediums complex. So the imaginary part of the refractive index is the absorption, which is this graph, and it's then by this dispersion, which is this. We are measuring this dispersion. This dispersion gives us the phase shift and rotation of the laser line. And since the rotation is directly proportional to this dispersion, and this dispersion, which is very hard to understand, this differential refractive index is directly proportional to the atomic alignment there. And hence by measuring the set of the language variables directly related to the beat, as we have seen from the previous slide. So by measuring this rotation, we can get a measure of magnetic field strength. So how we can anything this rotation is something like balance polarimetry. Uh, laser light then comes out of the radiant cell. We pass it through a Western prism. This Western prism divides the laser light into two perpendicular components, and we, without magnetic field, we keep it as the polarization to be 45 degrees so that the intensities of both the perpendicular components are equal and we get zero delta pi. Now, when magnetic field is applied, it rotates. So we get Ix and pi by component is like this. And we get some delta I, delta I gives us the iteration. And we are measuring this rotation. So this was our experimental setup. We had the median pattern over there, which is around Helmholtz coil. This Helmholtz coil applies the control magnetic field in the reading pattern. It was calibrated at 1.2 dots per ampere, and current source which was used was calibrated at 8 milliampere per volt. Then we were using a whole metal sheet to suppress ambient magnetic field and Earth's magnetic field. A laser light, we were using D2 line of radium because this so 780 nanometer laser was used. And the beam splitter was used to split it into two parts. One was going to the radium cell and one was situated absorption spectroscopy for adopting the laser at the resonant frequency and then posting just and differentiating. This was the spectroscopy. I used both the Helium 87 and Helium 85 isotopes for the spectroscopy. And for the further atomic magnitude, I was using Helium 87, and since I was getting more absorption over there, so this was the transition I used for atomic magnitude. So this is the most experiment I did. This is this S-shaped dispersion curve is what we call as NMR signal. So first I was plotting optical rotation with magnetic field with different medium, and I was getting maximum rotation for this green signal, which corresponds to the depth of this Doppler broadening spectrum. So with maximum absorption, I was getting the maximum rotation. So this is the point we were using for this to measure the optimum intensity for the magnetic field measurement. And for this, we see that as intensity of the laser light increases, the optical radiation is increasing, but it saturates at 1 milliwatt, and after 1 milliwatt, it was decreasing. And also, from the signal, we can see that I was applying the magnetic field from -5 microwatt to +5 microwatt, but at high magnetic field signal is saturated. So only very small magnetic field around -0.5 microdescam to 0.5 microdescam is a radiation linear signal. So this is the part our magnetic uses. Next, I take the frequency response for the magnetometer. So this is a new signal is the frequency response of magnetometer. You can see it is a clear roll off. We did this experiment 2 to 3 times and we were getting almost same thing. So then we also checked the frequency response of the current source we were using. It was almost meaningless. So this roll off just because of increasing magnitude responsibility still don't know why it was behaving like this. But still we were using the half rounding, we were able to get the value of around 23.7 kilo. Then I measured the sensitivity of the magnetometer. I was given 100 milliwatt input signal for the second. This is the intensity of the signal. And I was getting 78.28 millivolt signal with a noise of around 0.01% and voltage into magnetic field is 9.576 picotesla. So this is the sensitivity is 10 picotesla. So yes, the sensitivity is a magnetic that is sensitive to 10 picotesla. Which is very small magnetic field and compared to the Earth's magnetic field, which is a microscope. So yeah, this was the characteristics of the magnetometer. I also did modulation experiments. So modulation experiments, since when we see at very less frequencies, this noise is much more than at high frequencies. So to measure the signals which are in very low frequencies, we have very large noise. So we can shift it to the high frequencies and start using modulation. There are two types of modulation, amplitude and frequency. I did frequency modulations. I wasn't able to complete the amplitude modulation. So that's all. You have a pretty position.
So specifically, so many people talk about hertz. What is hertz? Where is hertz coming from?
It's because when we measure the when we are taking the signal, as the large signal we take for a longer period of time, signal we take, the when we average out for a large signal, the noise will be less. So the new signal we take, the less noise we get. So to standardize it, we are taking just one hertz signal, and then we are measuring the loss.
This is a very bandwidth possible. You just described the time modulation we added. What about the still has the bandwidth? Each squaring frequency. There is square root of words somewhere, right? Why square root?
That's what. So when we are taking the signal, we are taking it from the oscilloscope such that the signal we are doing NFP is just one hit signal. And then visually.
If there is something to do with knowledge, the encoded nature of it. It will also take for the so on. How does the media collaboration rotate on? Why is practical it's a different from two physics?
So we kind of factor in this system more.
It's given, let's say. It's given that for effective why should that amount to rotation to the universe?
It's like due to optical bombing and all, we are having this atomic alignment. This atomic alignment is changing the like there's some changes in the material. And when we see
It amounts to different interactive indices for the two surfaces. So you prepare the material so that it has this property. Now I shine light. So you put it into the origin.
the light will shine, that's why this is prepared.
Scientists are rotating. The polarization is rotating. Now the material has certain properties. If you see light in certain way. Now it has got the property where two circular polarizations are tilted differently to different spectral masses. Why should that amount to rotation of the linear plane.
And the circular means is rotating in this position. So it's because if two polarizations are facing different characteristics, the velocity will be different. And one is one will fast, one will move slow. So when we add them up, there will be some changes in the polarization.
What
When,
why is the addition?
when it comes out of the middle, it will be one line version of two separate lines.
Yes.
So when they superimpose,
So you're considering linear polarization as superposition of something?
it's superposition of right. So it's really good.
What is the reason why did you the video having forward and
It's because first is that the medium atom vaporizes very easily depending on 40 to 80 degrees Celsius. And also it also interacts very strongly with light. So we get very strong optical bounding using reading. And also the D1 and D2 line of the medium, which is around 790 nanometer and 785 nanometers. We can easily get these lasers if they guide the lasers. You know, I think all the sound is the mistake. That the question is. My name is Tamir, and I had a BBC talking about organizations. So we wanted to define artificial place in simple words. Yeah, the person found space like that property documents are displayed like and then get the full picture. Yes, there are some misconceptions on the current space that in general. So this is a question. So according to the business example, gravitation is a curvature of space time and not of force. According to Einstein, so we need to understand what differentiates the classical and the relativistic descriptions of gravity. And this is everything you know we understand field. So according to Newton, when we understand concepts, if we consider the example of evolving around the something. This is centimeter force gravity, which is applicable to centimeter some, and then the point is trying to escape and this tangential velocity, which is causing it to get this alright. So, but according to Einstein, we also identify space time is that and not meaning with a certain cost and possibly in space. Now the introduction of the sun, of course, space time occurred. And the Earth is merely moving in an inversion it's moving inertially in Earth space. There is a force which is acting on the aspects. So this curved path is actually the geodesic of it. What is a geodesic? It is a straight non-accelerated path Earth space. And a simple example to understand geodesics is that generally on the airplane just run on a flat map. So it would appear to us that this is the shortest path between the two points, but on curved geometry, this would actually be the shortest distance. So what occurred to Einstein was that in free fall, no force would act in the body, and this is why we feel the sensation of weightlessness. According to Einstein, when we are standing, the ground is actually accelerating us upwards, which is preventing our path towards the center of the earth, and that is our natural changes. These are Einstein's field equations. So given the tensor relation. So they relate space-time curvature to the distribution of matter and energy. And this over here is the Einstein tensor. This represents the curvature of space-time. This is the cosmological constant. This is a metric tensor which would not a distance between any two points in space. This is a coupling constant, and this tells us that it takes a large amount of mass and energy for space-time to curve. And since this stress energy tensor, which represents matter, energy, pressure, and heat. So summarize. Yeah, so this we already covered in the example. First transition is from flat to first loop. And the second transition from classical to realistic notions of gravity would be the notion of 3D space and either specific entities to a 4D space time. Okay, so what happens when what kind of space time in a body with significant mass accelerates? So this will cause a disturbance in the gravitational field or the curvature of space time, and it is this outward propagating updated space time that we are perceiving as gravitational waves. What kind of waves are gravitational waves? Gravitational waves are transverse waves, which basically means that if the wave is propagating down an extension, that it can be press around if you consider this z direction, and then it will expand along the y direction and get so here we have formula of the white mass, it's gravitational field. So we can lots of places. Gravitational waves are not they are not local waves because of the law of mass energy conservation. Local waves are basically a monopole based source which should be emitting radiation radially or radius electric field. And gravitational waves cannot be monopole waves because let's say if we consider mass, the mass cannot spontaneously increase and decrease, which obviously violating of conservation of mass energy. Even if the body pulsates, which basically means it expands and contracts. According to Kirchhoff's theorem, the total mass of the object will still be constant, even if it expands and contracts. So the gravitational phase actually remains static. And gravitational waves cannot be dipole waves either. Same with electromagnetic waves. You have a charged dipole, and both the charges can move relative to one another while keeping their center of mass fixed. But then we cannot achieve this with gravitational, we cannot achieve gravitational waves because mass cannot be negative. And the center of mass of an isolated system cannot accelerate on itself. So it's not possible to get waves. So gravitational waves are actually they're protocol relations because they require asymmetrically changing mass distributions or changing mass for the whole group. So the cosmic events that actually can generate gravitational waves. They happen very far from us, and by the time they reach us, their effect is quite tiny. How do we detect gravitational waves? Now, I will take us how to talk about two elaborate cause detection. From Einstein's prediction to design working and discovery of gravitational waves. The first prediction, a new and a difference.
In the early morning of 14 September 2015, almost 100 years after Einstein was discovered the relativity, the scientists at the lab of scientific collaboration detected a tiny ripples in space called gravitational waves for the very first time. We can see this separation. When the two black holes come together, they disperse faster and faster, producing the gravitational waves and releasing the energy just from the three cells. One of the creator of the light and Nobel laureate described the detection of gravitational waves requiring the precision almost equally precision, but he compared it to the measuring the distance of Earth from the sun, from the Earth to the accuracy of a single atom. But this is an important question. How do we detect them? How do we detect something so incredibly small from so far away? Here comes a light concept. The world's most precise measuring instruments. Measuring LIGO stand for Laser Interferometer Gravitational Wave Observatory. It is one of the most sophisticated physics experiments ever done. Spearheaded by Nobel Prize winner Benedict Steve Warren Daniel, the setup consists of two giant interferometers, one located thousands of kilometers apart, one in Jerusalem and one in Israel. As we can see here, it is a diagram of a iPhone light. Now let's go inside the language. The components are configured. The basic design of light was built on the modified meters and interferometer. Each detector has two arms. As we can see here, each detector has two arms, so 4 kilometer long. Pass the laser into it, it gets reflected into the field. Two arms, one for here and one for there. And after reflecting from the test mask, it will come from both here and get detected by the sun. In the lens. The lens of the arm of the interferometer, which is light, which is 4 kilometers from here and here, are precisely adjusted. So that when the light falls after reflecting from the mirrors, they will go under the destructive interference, producing more light around the detector in normal radius. And when a gravitational waves pass through the interferometer, it causes the spin, stretching and compressing of the interferometers. When the gravitational waves pass through it, it causes the stretching and compressing of the interferometer, and which changes the phase between the waves, and they will go around constructive interference and produce some light on them. Light from this gravitational wave seems like a string formula, which is very small, which is less than the change in the interferometer arms is less than the size of one proton. Making it one of the most precise experiments ever did. And from a view of the significance of beta to 150 is that when it was produced by a model of black holes forming a single black holes, the solar masses, and around 3 solar masses were produced in the universe, making it 50 times brighter than all the stars combined. Are we sure that the gravitational wave swinging for the real astrophysical? And the answer is yes. They are the strong, they are the, because there are 5 strong reasons for this. The first one is dual side consistency. The interferometer is located in Harvard and Livingston, so exactly the same pattern when the gravitational waves pass through, as we can see here. And the second is a 10 millisecond time of flight. The signal arrives with a 10 millisecond of delay. At the Harvard and Livingston, there is the light takes from here to here with 10 seconds. And exactly the gravitation wave detected at Harvard, and after the 10 seconds, it is detected in Livingston.
So what are we saying? Feeling kind of like like time, like travel times.
Right, it's really that the distance usually happen in the distance. The light usually takes 10 milliseconds to cross from alpha to the distance. And the gravitational distance that really seconds the distance. Then
You know the distance separation.
so I exactly don't know the distance, but they are the
Suppose like, can there be a situation where the signal came from a particular direction and it reached both of them at the same time? There's no delay. Can it happen?
so it doesn't really time spoken in the
Why do we do? Why do we do what?
So there is a geographical condition also that this place is somewhat geographically as place described that I can real time
They found the two extremities in their country, that's all. One is north, west, other is south. People, that's the largest they could get, so that's where. But why do you what? In fact, they are now building third in India also. They want even more. Why? They speak the same thing again and again.
See, the shifts are according to what is the reason for the shift. Why can you make simples? Why not 20? Why not 5? Why not 0?
distance there is no
In 10 milliseconds, time to speed up light. Is the distance between these two locations? Is that the argument of place? I'm just trying to understand.
measure firstly we are given in after and after there are things to be
You mentioned something related to twice the relation of three suns. Yes, sir.
so even the very low levels comparison. The one is of the 26 solar masses and one is of the and one is of the 62 solar masses. The thing is solar masses, one is of the 32 solar masses. And after they combine, their total solar masses was 3 solar masses less than their combined solar masses. And then these solar masses are readily converted into gravitation waves, which is the pattern of the universe.
So it's commensurate with the level of the signal on XU. That is so. Then can one find out actually how distant the source is?
It's only us.
We go through.
So it was 1.3 billion years ago. It was nearly one. Yes, of course, it was before we went up at 1.3 billion years ago.
It would be 1.2 million light years away from us. This is
Before the gravity.
there's the book questions to the audience.
I have. I know. So okay, it's not your fault. So for me, gravitation is a new idea. So what is like physically represent? Like if I talk about light, it's a EM wave actually. So what is gravitational wave usually, and how the process of your inference is calculate that wave?
Basically, but there are gravitational waves and the mathematical explain the gravitation waves come together
If the compresses the compress of the dimension in one direction and elongates the dimension in one direction. Yes. As it travels throughout the space, let's suppose it is an XY Z. But it travels through the in the basically the it basically it is traveling in the direction and this is that direction. This is that direction. And when it travels in this direction, it is a chromatic gravitational wave direction. It expands the space in one direction and compresses the space in one direction. When you compress or elongate that so that's your travel. Then we travel quickly on one. यहाँ से area has to increase due to gravitational waves here, and the gravitational waves get reflected into two parts. Here, there is a beam splitter here, and it gets reflected in one part of the splitter here and one part of the splitter. And when the gravitational waves pass through it, so वो pass through it, तो क्या gravitational wave बढ़ती है जो space है इसको stretch कर इसको compress करके उसको stretch करके जो वो gravitational waves वहाँ से travel की और पहले तो पूरा 4 किलोमीटर करते हैं. But when gravitational waves pass through it, it stretches the space in this direction and compresses it in this direction. So the waves have to travel a different direction. Here the waves instead of the direction is when it covers a distance larger than 4 kilometers.
And let's see.
We will take a short bit now for sessions. Please tell us. And we'll even be complete at around 4. We now have problem and action in scientific scholars presenting a macroscopic data spectral based background oriented theory.
Good afternoon to one and all present. Today, I, Akshay Bhatia, and my friend Robin Dent will present to you our research work on macroscopy with laser speckle-based background oriented study. Now we all know that invisible objects are impossible to see by the naked eye. But what if I told you that there is a method by which we can see the invisible? Yes, that is Schleiden technique. Herein, we utilize the refractive gradients that such transparent media introduce in order to visualize them. As you can see in this example, when hot air from a candle flame has been seen through Schleiden. Let me explain this further by drawing example from a standard mirror-based Schleiden setup. Here, light from a source is focused by a mirror onto a tip of a knife edge or any other obstacle behind which an imaging system is placed. When I put a fake object in the path of light, the light is bent, due to which they pass over the obstacle and enter our imaging system. Hence, refractive gradients are translated into amplitude differences, allowing us to see the invisible. Over the years, scientists have come up with many new ways of doing sharing, and a unique variant is background oriented sharing or BOS. Here, why is it unique? Because it reconstructs the flow after taking the images by post processing them through certain algorithms. Hence, it's also known as synthetic sharing. Herein, we use a background which we place behind our face object and we take images of the background. Now, due to the refractive gradients, the image of the spot on the background appears to be shifted. And then we can map these shifts through algorithms to reconstruct our face object. The background has to be high contrast, well illuminated and random, and each point has to be distinguishable. BOS has been traditionally used for large scale flow visualization. For example, as you can see, where a large wall or forest meets, or trees have been used as natural backgrounds to visualize these large scale flows.
Now, as Akshay mentioned, UOS is traditionally used for large samples and large backgrounds because it gives us a large field of view. Our work was to see if we can apply the same technique to a very small macroscopic sample. Now, this poses certain challenges. The first of which is that since the size of the sample is so small, the background that we will use, its size, the size of that pattern, will also be very small because it has to be comparable in size to the sort of shift that the sample produces. Now, procuring or generating such a background is a problem. The second challenge was that since the sample is very small, the imaging system would have to zoom a lot to view it, and that would reduce the depth of the field by a lot. So that means that the imaging system, the sample, and the background would have to be placed in that narrow depth of field, and that would make the setup very cluttered and disastrous. So what is the solution? How do we solve this? The first problem was solved by using laser speckles as our background, laser speckles that are generated by passing laser light through a diffusing surface, and we use that as a background. Why? Because those laser speckles are random, high in contrast, and most importantly, their size is reasonably small, but also that their size is controllable. You can make it smaller or larger by manipulating the imaging geometry. So that property is very useful for our work. The second problem was solved using a telephoto lens attachment to our imaging system to extend the center so that it is no longer cluttered. One important thing to note here is that the algorithms that we use, two algorithms for our processing, both of them are executed on a smartphone. The first algorithm, optical flow, is executed in the Pocket Schlerin app that was developed at IIT Delhi by the team of the professor under which we love. And the second algorithm for cross correlation was made by us only, and we also made a user-friendly GUI, which, if the time permits, I'd love to demonstrate to you. Now, laser speckles are of two types, subjective and objective, and both of them have their different properties. So we use for our work subjective speckles. Why? Because subjective speckles give us a one-to-one correlation between the background that we are imaging and its image, which is what we want, so that we can see the local variations. This is something that we do not get with objective speckles. Now, this is the, I guess this is not very clear, but this is the sort of images that we took. Like in this is the speckles you can see. Now, this image is obviously, when we took it, this is zoomed, and this region is further more magnified. I'm sorry if the image is not very clear. So, you can just imagine this, how small the speckles actually are that you're working with.
Now let us see how we actually make our setup in order to do such small scale BOS. As you can see, we use a standard 650 nanometer laser pointer and put a scotch tape on it, which acts as a diffuser. The diffused light is then reflected by a mirror towards the imaging system. As for a sample, we use a very dilute sugar solution, that is 1.62 gram of sugar and 27.5 ml of water, and put a single drop of this in a petri dish containing water and take images with our smartphone to which we have attached a telephoto lens. Now, one thing to note here is that our setup is extremely cost friendly. Traditional viewers using high cost cameras in order to visualize, but we have just used an Android smartphone, and even the processing happens on the smartphone itself, as Robin described earlier. Similarly, our other apparatus is also just household items, which can be easily procured. So we have significantly reduced the cost of doing viewers and made it widely reproducible. Now, once we have taken the images, we need to process them, and we do this by two methods. First is optical flow. Here, we assume that pixel intensities remain constant between two frames and that neighboring pixels have similar motion. So then we can write this equation and solve it in order to get the flow velocity and hence the displacement component. We solve this using the Gunnar-Parnevak OF method, which is a dense OF method that calculates the per pixel displacement, which is more suitable for our work. The second method is cross correlation. Its basic principle is that we take a patch in our image and or the interrogation window and sweep it pixel by pixel in a slightly larger patch in a subsequent image and calculate the normalized cross correlation coefficient whose value can range from -1 to 1. These basically tell us how well our pattern matches between the interrogation window and the search window. So if there is a phase object, there will be refractive variance and hence there will be less matching. So the value of the coefficient will be less. So if I plot the coefficient values for the entire image, I can reconstruct the phase object.
Now let's have a look at the results of our experiment. As you can clearly see, we are able to observe the flow of the sample as it changes with time. The first row of results is with optical flow algorithm and the second is with cross correlation algorithm. Now let's compare these results to see which algorithm works better for us. We do this by making surface intensity plots of the two results. As you can clearly see here at the first glance, that the region where the sample is present, we have reasonable intensity in both the algorithms. But one important thing to note here is that the region, the neighboring region where the sample is not present. In the case of cross correlation, that region is easily distinguishable. But in the case of optical flow, you can see that there are many false peaks present here. This is undesirable. This means that cross correlation provides us with better results and more information as compared to optical flow for laser speckle based background oriented sharing region. Now we have said multiple times, both here and I have said multiple times how our setup is cost friendly and how the processing is done on a smartphone. So this means that our experiment, our method is very reproducible and it has many educational applications among several other applications. But one future possibility that we ourselves want to explore is US microscopy. Can we make this? Can we use this method for a sample that is much smaller? Up till now, the smallest sample that we have imaged is the 170 micron thick cover slip, as you can see here. And so, but like this is where that actually the cover slip is in the result, but it was not really visible. So this is what we have successfully measured. That is the smallest that we have measured sample up till now. Daphnia or water flea is a live sample that is its organs are much smaller than this. So that is something that we hope to image in the future. So that would come in the domain of microscopy. As you can see, the body of Daphnia, it is commonly found in lakes and ponds. The body of Daphnia is completely transparent. So we can try to image it. And since it would be live, it would move around. So it would be a dynamic sample. So it's perfect for our work. So we can try to image its organs. For example, its heart, which has the diameter of roughly 50 microns. So as promised, let's have a demonstration of our GI. This is the collab file that we have in our program. We have also tried running this in a smartphone, any smartphone, so it can be easily run in any smartphone and it gives me very good results. So this is the simple interface that we have made. You do not need to know anything about cross correlation or how the algorithm works. All you need are two images that you have taken of the subsequent images time separated, and you just put it, and it will give you your result in a few seconds. There are some parameters as you can see here, but you need not know much about them. Even if you want to, they are very simple concepts to know. But even if you don't want to, you don't have to. You can just play with it and see what you get. You can play with it and see which gives you better results. So as you can see, we have constructed the flow using the two images. So these are the references. We'd like to express our sincere gratitude to Professor Manish Kumar at IIT Delhi and Professor Gitanjali Sethi at Sanskrit College for their valuable guidance and support on this work. Thank you.
So now we can do the question and answer session.
Like we said, you use two algorithms, whoever or like I in the target object. And also direction methods.
Thanks, Pritesh.
Um,
Use sharper changes. Sharp. Slope correcting.
That is not the scope of our works, but there are many ways to do it. I'm sure we can explore them. Like there is another algorithm like CFS, which is consecutive frame subtraction. It gives much bigger results, but it's a very simple and it's used for mainly qualitative purposes. So there are many ways to do it. So like for CFS, if I give an example, like the application that was developed at IIT, they use CFS to give you live results. Like you can have a sample and you can just open CFS, like you can do a video of that. You do not need to.
So how's the reconstruction actually done?
So, if we have the
What is the magic? You understand the cross correlation, right?
So, if well, if our cross correlation, my reflective will be this present, and I have imaged the starting two images of the diagram at some time interval. And due to my refractive wavelength, there is bending of light. So the same spot appears at a different place.
Correct.
So my cross correlation coefficient for that spot will have a lesser value and the spots where the refractive gradient was not present. So when we plot that, we can get the when we got the magnitude of the coefficient for the entire image that we did. Yeah. So here the values were less. So that is where you
So you will get shifts.
yes.
Yes.
You will get map of the shifts.
Yes.
Yes.
What does that do? It's a map of shape. How do you translate this?
So if we have we get the coefficients for different interrogation rules, right? Different patches in the image. So if we have a lower value for that cross correlation coefficient, this means that it has shifted. Like it's basically template matching. So where there is no
I mean, you wouldn't just leave it at low cross correlation. You would also shift it and find out the shift at which the correlation maximizes.
yeah, that also can be that also can be.
So you will get a map of shifts.
Yeah. So like the shift itself, you can also find that.
So we have the equal B. These are the shifts. And if we find the maximum, the best shift for the best image.
Correct.
We find the best shift.
Small patch wise.
Exactly. So like if you have
I'm saying what you do is the map of shifts.
exactly. So if you have like let's say you have a search window, this is let's say a small patch in the second image. So from the first image, you take a smaller patch. Like these are in the same regions. It's not like if you have the entire, it's not that the intermission window is a patch from there and it's a form patch from there. You take it slightly larger because what they're working with, it would be minute shift. So the point of the speckle will not move from here to here. So we'll just take slightly larger. What we'll do is that we do template matching by cross correlation. We'll save the image and we will put it there. And we see how good of a match it is. Then you shift it a little.
Yeah, I mean, systematic search.
Exactly.
The entire shift range.
Exactly.
Okay, the shift range is limited because for physical considerations that
Yes.
things would migrate from
Yes.
here.
And that is actually one
we gotten that shift map.
Mm.
What is? Or the shift map itself is the information. Is that what is plotted in this images?
So we find for a particular search window, we find the maximum value of the correlation that we get. So if it has not shifted, that would be very good. So that means that nothing has happened. It is a proper match. Nothing has happened there. There is no shift. But when there is a shift, so it will not be a very good match. So the maximum value itself will also be very low. So the cross correlation coefficient would be less. But even after that, you can actually find the actual shift that has happened. You can also find that the displacements.
Yes.
So
At which the correlation will be very high.
yes. So like for example, let's say this is a point that in the this is a speckle and this will be shifted by the speed. So you can actually find how much this is. You can actually find the displacement as well, and you can make further like there are other algorithms, and you do a lot of processing to actually find quantitative results as well. What is the refractive index of of the sample that you're having? How much shift you have, where you have it, and all those things you can find.
Why do you need the random background? What's the randomness supposed to do here?
If all the points are the same,
No, there could be a grid. It can be a pattern rather than the random.
it will be difficult for the algorithm to know that if some gradient is present and it can confuse between two points. If there is a pattern there, then
Exactly. So it can give you false matches. If there is a periodicity, it can give you false matches. If it shifts by, let's say it shifts by a certain amount, and if it's a periodic pattern, and it again comes to that periodic part. So it can give you a match. But that
If
is
it's a uniform, then
sorry,
if it's a uniform background, then
completely single color.
Yeah.
So then, like how will
shift will show
no how
because your effective index is changing, right? So it will show in some.
how do we subtract it because there is no difference between the two. Like it's just say completely black, then both the images are completely identical.
No, but the effective index of the medium is changing.
But still, the algorithm does not know that.
but we are imaging only the background. If the background is just plain, even if refraction happens for the in the computer, the two images will be exactly the same because there is nothing in the background. There is no distinguishability there. It's plain. So even if
No, the way I understand is the background, the median, right? When you're getting the light through the median. Yeah.
Yes.
Median is changed. So what we're recording should change. It should be the same.
But see, we are imaging the background. The medium is transparent, so it will not be visible in our images. As you can see, it will not be visible in the images. So if the background is completely uniform, if it is completely one color, and you take the images, there is no difference between the. Like you are saying that the refractive index will change. I agree, but the algorithm does not know that. The algorithm only has the images.
Question of section. I like to talk. I not like to talk about this. I'm not like to talk about this. I'm not. Completely because I'm not that.
Yes, it's I think probably what is it?
It is bad. And I try to come tomorrow. But I will update you. I will first share my presentation with you. Once it is ready, I will share it. So I will first share it with you.
Thank you.
Systematic update, which go to state maybe no coordination. It will make sure, I'm saying it's integrate the pattern. If you go into the pattern. Not maybe the two people, let's say. Remove your uniform pattern. Systematically taking it down.
Spacecrafts and satellites to establish large system because the solar system. It involves a satellite or a spacecraft flying past a planet, and it alters the direction as well as the speed of the satellite. We will analyze the change in velocity with respect to the inline parameter as well as the incoming speed of the satellite. It has also been used in the Voyager mission. So we'll first take a look at the single diffraction by 90 degrees. So we have this is a reference frame of the planet, and in the reference frame of the planet is at rest, and the sun is somewhere in the negative y-axis, and the satellite is approaching the planet from the negative y-axis and gets reflected for 90 degrees and towards the positive acceleration. And is the initial velocity of the satellite, and is the final velocity of the satellite, and we have similar vector algebra, which gives the equations for all these velocities. And we find that the magnitude of the initial velocity and final velocity of the satellite is the same. It comes from the fact that when we create the moment of acceleration equation, since the mass of the satellite is very much less than the mass of the mass of the satellite is very much less than the mass of the planet, the specific change of the planet is very much. So we find that the magnitude of the satellite, when it is reflected by 90 degrees, the magnitude of velocity of the satellite is almost same. The previous case was for the reference frame was in the frame of reference. Now let's look at the same case in the velocity frame of reference. Here the planet is moving in a the planet has a in the previous case the planet was not moving, and in this case the planet is moving with the velocity v. And then assuming the planet is moving in a straight line, because the movement takes place in a few days as compared to the revolution of the planet, which takes years to happen. So we have remember choosing the initial velocity of the satellite, and we attach as the final velocity of the satellite. And by simple vector algebra, we have this x component that is added to all this as compared to the previous one, and we find the change in the velocity. That will get us delta one equal to by simple vector algebra. There we have three cases where u is equal to u3, where the change in velocity is very slight, and then the velocity of the incoming velocity of the satellite is reduced from the outgoing velocity of the planet. The change in velocity may be equal to the orbital velocity of the planet, and then the velocity of the satellite is reduced less than the velocity of the orbital velocity of the planet. The change in velocity is nearly equal to the initial velocity of the cyclic as if there is a bound, the change in the increase in the velocity of the cyclic does not exceed the orbital velocity of the planet.
So I'll be talking about the scattering effect. So basically, okay. So firstly, I'd like to explain certain parameters. Beta is the angle that the velocity vector of the spacecraft makes with the negative x-axis, and gamma is the angle of scattering. Now we look at the in the Planck's frame of reference, we look at the velocities. These are the components. Now we find that the change in the velocity in the Planck's frame of reference would come out to be zero. But when we move on to the heliocentric frame of reference, in the x components, we'll be adding the planet's velocity with respect to the sun. So we'll be getting these values for the velocities. Now we find a change in velocity, and finally we get this expression for the change in velocity. Now we plug in k is equal to UV by UM just to simplify the expression, and we get this expression. Now, from this expression, we can see that beta needs to be between 0 and 90 degrees, and gamma needs to be between 0 and 180 degrees for there to be a gain in velocity. Now, now I'll be trying to find out the relationship between scattering angle, gamma, and the impact parameter. Now, up until now, our result has been independent of the nature of interaction, which is the gravitational inverse square law. So now we'll be finding out the relationship, we'll be incorporating gravity here. So first we have a conserved quantity, which is the energy, which for large distances, the total mechanical energy would be equal to the kinetic energy only. And we have the angular momentum. This is the orbital equation, and this value epsilon is the eccentricity, which is found by this equation. Now, for U effective in the two-body problem, the formula comes out to be minus C by R plus L square by 2m R square, where C is G N M. So we differentiate that equation and we find the minimum value of R naught. We differentiated with respect to R, and we find the minimum value of R, which comes out to be L square by MC. And we plug that value of R and we get this for the minimum value of U. We plug in the value of E and the value of minimum U to this eccentricity equation and find the expression for eccentricity. Now, in the case of scattering, as R tends to infinity, 1 plus epsilon cos beta tends to 0. And cos beta is equal to this value. So, finally, we get sin gamma equal to 1 by epsilon, and tan gamma by 2 comes out to be this 1 by under root epsilon square minus 1. We plug in the value for epsilon that we found here, and we get this expression for tan gamma by 2 is equal to gn by du square. And now, from the geometry of the figure, we can see that the relationship in beta and gamma comes out to be beta is pi minus gamma by 2. So we plug that in the expression for delta un that we have here. And so we get this in terms of sine gamma by 2. And ultimately, we use the relationship tan gamma by 2 is equal to gn by d1 squared equal to d, which then using that we find the equation for sine gamma by 2 in terms of d. We give this quantity a name s and we plug this in our equation. Finally, we get delta un as a function of k and d, where k is the ratio of the planet's velocity to the satellite's velocity, and d is gn by dun squared, where d is in capital. Now,
So now that we have the expression of delta U as a function of k and d, which is associated with the incoming velocity and the impact vector respectively, we can now try to find the variation in delta U as a function of those things. So first of all, we're going to non-dimensionalize the equations by dividing it by a matrix scale factor, which is the velocity of the planet, ut, and we introduce x is equal to u1 by up, which makes k is equal to 1 by x and d is equal to 1 by lambda x square, where lambda comes out with a non-dimensional impact factor. So then we have our non-dimensional delta un. In order to study relation to impact parameter, we fix the value of incoming velocity and in vary impact parameter over range of values. Here we see that the maximum increase in delta in velocity is at the lowest value of impact parameter in our range. Because as impact parameter tends to zero, there is going to be a higher velocity. However, the impact parameter cannot be very small because of the distance of force approach. It has to be greater than the radius of the pattern and the minimum distance. So the optimal lambda comes out to be whatever minimum allowed impact parameter that is. And then for relation to the incoming speed, we basically express delta U as a function of u. And here you can see that there is a pre-factor x in the expression, which and by increasing incoming velocity, we also increase delta U1, but that decreases the deflection angle, starting angle gamma, because of which they kind of cancel each other's effect out, and which is why for very small incoming velocity and for very large velocity, we don't have a very high increase, and so we get an optimal value somewhere in between. Uh, Finally, we're going to apply an analysis that try to validate it by applying it to Voyager to remember around Jupiter. Voyager to perform analysis experiments around Jupiter, Saturn, Venus, and Neptune. And before crossing Jupiter, its velocity was less than the escape velocity of the solar system. And after crossing Jupiter, it went above the escape velocity, which is why it able to travel to distance. So for given heliocentric velocity at the angular approach alpha, with respect to the sun, we are able to calculate we are able to calculate u1 and beta with respect to the track. And we did not use the data directly from Voyager to gravitate as model because it was hard to understand. But instead, we took the approximate values of our parameters from a particle in the dimensional physics that we have represented. And using all of these approximate values, we are able to plot a graph between delta U and the angular approach with respect to the in the pattern of the sun. And for an angular approach around 45 degrees, which is what was the case for altitude, we get an increase of speed of 11.2 kilometers per second, which is a reasonable result for our estimate because it should be somewhere around 10 kilometers per second. And that's all. And we would now I would like to talk about some of the limitations of our analysis. First of all, it assumes that a planet is going in a straight line and over the course of the planet, and that it has a constant velocity, which ignores the true orbital curvature and slightly alters gamma. And it also, we are only considering this to be a two-body problem, where between a spacecraft and a planet, where the spacecraft basically analyze the change in the speed and also try to optimize it, but we don't really focus on the deflection and where it is going to go after it has increased speed. Uh, to the next planet that's going to go. So because I'm going to include 3 body problem, we want to do that. So because of this, it cannot be really applied to a real life scenario of the plan, right? However, if it's something that we can do in the future, that's it. So now I can clear my session.
Will it optimize on the energy spent for amount of energy supplied,
The amount
like the
as to the income speed and the time. We I do not
yeah, for the flyby to happen in certain way. We try to minimize the energy to be used.
the energy that we require for the many no, we have
Suppose it's a satellite.
that the satellite is going to go consume it. So we haven't really tried to optimize. We haven't tried to like save any fuel. We haven't tried to. We just trying to see what parameters we should able to the difference in order to have the maximum change in speed. So we haven't really focused on whether we should do a lot of stuff.
Or at least it will be something in terms of initial speed,
Yes.
one way or straight lines,
Yes.
right? So that's which area that you start with that. So we find really optimizing to that. Not, not
Can you explain how this Coriolis force and centrifugal force they talked about, they will come into the picture?
So this motion centrifugal force, basically they show up when we consider the third body because when they don't use there's a lot of ways to go about it, but for example, if we take a rotating plate to the sun as the reference, that is when we are going to introduce Coriolis force and centrifugal force. If we have it very precisely, hypothetically,
As I understand, we make a coordinate system transition from Helios from the planet frame to the sun frame.
Yeah.
So there doesn't have to be sun as such in your analysis, right? It's just a frame.
Yeah.
And so where does that coordinate transformation you're doing anyway, right? Where are you missing the Coriolis force and centrifugal force? Centrifugal force. You said you're missing it, right? You're missing it. You are missing it, but how? So how you could have incorporated the food so that you don't miss it?
um,
I'm making myself clear. You, as I get it, you are stating that you have not included these two courses, right?
yes.
So I'm asking what you could have done to include these two courses.
I had this one confusion. The initial all the situation that the show initially you started with the money. Those are I mean, the asymptotic behavior is the important. Right?
Yes.
It's not the detail. People is really need to take that track.
Right.
Hmm? It might have given people that impression.
Right now, the philosophy much before the
Correct, correct.
Yes.
The depiction was not of the what happens in it.
Yes, it was just very fun. Yeah. It was just to show the coordinates experience. Yes.
What kind of curve it would have been? Actually, you do something, but you got to take this into account. Exactly what kind of curve it would have been?
It's really either with the colors.
That, will that also correspond to the shortest path?
The shortest part.
When all these go from this place to that place. Is that the shortest path in the presence of the planet?
No, it doesn't because it basically you want to save fuel. So in order to save fuel sometimes like the fuel that you spend on going to the planet in order to form the gravitational field is it depends if it is worth it.
I'm saying, is there the principle of least action molecule? In the presence of course, the gravity of bodies placed.
I don't, I don't.
No, they are first year. They
Sorry.
But I think
is the
Oh, okay. I'm not certain, yeah. Right.
You just said.
Shiva Nayan's
That's nice.
This is not a question that it's.
Okay. No, no, yeah, in a way. Like the light travels to, your snail's law and derive, right?
At least another planet takes to the need to be.
Minimizes that, right?
And
Although it might appear like long path compared to the straight line if I have drawn. Even the medium, that is the path. Okay? So similarly here, even the planet, okay, to go from this point to that point. Is that the shortest path? given the initial conditions, we could always, completely bypass the planet and go there. Is there any principle like that that emerges out? Actually, I'm just curious. So I'm sorry for taking out of the way.
No more question to the audience. I just want to make it keep coming.
I know the I now want to call Australian because I want the mapping on mapping the linear function. Characterizing not enough capital, but I found the figure inside this in this.
Good afternoon, everyone. Myself, Ashwin Satri, and I'm from Socials for and I'm doing my third year bachelor's in this college in BSc Physical Science and Computer Science. So yeah, this is my topic: mapping the Wigner function, characterizing non-classicality via quantum computer tomography. So before I start, I like to read a quote. So you might be familiar with this quote. Radio has no future. Heavier than air flight machines are impossible. X-rays will prove to be wrong. Do you have any idea of what's that? So, okay, yeah, it was by Francis Locke Kepler in 1899. So yeah, actually, it's a theoretical framework. It is not. It's actually impossible for the technical. So the technicality is impossible. So, but the theoretical framework is kind of cautious. Yes, it can be happen, but we don't have the technology right now for implementing the theoretical framework. So yeah. So as you can see, I mentioned some technical terms. So for the audience to make it clear, so I'll be defining the Wigner negativity or Wigner function. So Wigner function is Wigner negativity serves not only as a classical characteristic, but also as a necessary resource for achieving computational advantages in quantum computing. Also, the as a definition, I would like to say that Wigner function is a quasi-probability distribution function using a phase formalization of quantum mechanics. Its ability to exhibit negativity, uh, like its ability to exhibit negativity distributions is quantum behavior from classical. So yeah, so that was my introduction. So the theoretical framework, as I said, like, so yeah. As you all know, the classical CT scan, the computer tomography scan, is basically of photons radiating to the human body. For taking the from the medical background, we know that like if you are a diabetic person or pediatric person, we need to do some CT scans for like fracture. We need to do CT scans, and CT scans are like even though it's effective, but it has its drawbacks. Like we need more radiation, and the radiation causes very negative effects for the human body.
So I like to introduce a quantum computer tomography in which the what I say the radiation and also implicates its efficiency by image resolution also is like it's more compared to the classical CT scan. So as I mentioned earlier, it is abide by the quantum standard quantum limit SQ. And the n is the factor number of photons that emitted from the machine to the given object during the body. And its higher resolution requires more photons, and more photons means higher radiation dose. And they are critical for like patients, pediatric or Parkinson's or any like any person. So the trade-off is basically better images, we need more radiation. So it's the drawback of classical CT scan. So I'm suggesting, since cautious is that I said, suggesting a framework that's known as a quantum computer tomography. So let's dive deep into it. So the core concept is that exploit, exploit in the sense like using it for good purpose. Non-classical sets of light is surpass the standard quantum level. So as I said before, classical light needs coloring states the light lasers like it's an axis lasers for taking the size of 3D objects and making the reconstruction into an image form. So it has a short noise. Like if you are seeing CT scans, you can say that it's very black and like needed. Like you need to keep in a very way to look into that CT scans report and analyze it. Then it's mostly field space distribution. Also, it's the characterization and in the quantum light, it views the screens for characteristics and it also enables the Heisenberg limit, which is the like minus n to the power minus 3 or 1 by n to the power root minus 1 by 3 by 2. So negative Wigner function also enables us to know that there is a positive probability, like the probability is negative, enabling that it's just a non-classical story. So yeah, the key signature is Wigner identity for non-classical. So I'm not diving deep into the mathematical thing because I'm also a bachelor student and it's bigger. It's kind of a higher mathematics and I'm not in honors in mathematics, so it's difficult. But I understand the background topics behind it, but not in the deep way of mathematical foundations. So here, X and P are the momentum and phase. I'm sorry, position and momentum, and so this is the formula for the Wigner function, like phase-space quantum mechanics. It's a real value Corsi distribution system, and it's normalized into position and momentum to get unity that's increasing this efficiency. And it can be negative, as I said before, it can be negative. So it implicates the non-classical existence of non-classical sequences. So and so these are the like theoretical mathematical thing behind it. So quadrature operators and so yeah, measurement protocols like measure the quadrature at phase theta and like the momentum and position of the atom state level and collect the statistics and reconstruction like using the inverse Laurent transformation. Also that is above my scope of specificity, so I won't be diving deep. So yeah, like using after that we get the final uh, like interaction free measurement and interaction free imaging. Like it's all as forward to say it's also interaction free and interaction. It's interaction free measurement and interaction free imaging. So some historical stuff that I would like to discuss. So in Reining suggested the negative result measurement in which the non-observant without like the observance we take the we can take the observations without disturbing the quantum system. And also, next to that, Dick also uh, uh, suggested some non-scattering effects of atomic wave function. And also, it's a very famous, like during the Manhattan Project, these were used like the Elixir Weightman bomb testing detection system. So it's like in the I think I'm not sure 1990, the Elixir Weightman suggested a theoretical foundation of testing a quantum, like the nuclear bomb actually. Uh, to test, it can be detonated at a specific time or not, and it gives the maximum efficiency of 50%. And its applications were also like max and the interferometer, and and as I said before, it is ultra sensitive bomb testing. So this is the reconstruction formula. And yeah, and these are the mathematical foundations I'm not getting into. It can be more into. So yeah, it also measures the negativity volume, negativity depth, and quantum efficient coefficient. Got it? Uh, yeah, these were the differences. Classical quantum and optimal scaling laws in SAS code. Uh, yeah, Wigner functions of quantum series. I have generated a computational, computer management math flow. I generated one system which which gives the fork state, one to current state, and squid state and cat state. So six states, different states, and its metric values. So fork states are kind of a ring structure. I will be showing the diagram later. And Vaccinal components are fully positive, and cascades are strong interference matrix. So these are the metrics that I got from my simulation. Uh, yeah, this is the comparison, sensitivity and isotopes. Also, as I said before, it reduces the radiation. So this is simple formula that in number of quantum that we put in by the n classical, we get that dose is reduced by a factor of I guess 2 to 10 x factor. So yeah, 10 to the power 10 photons. Like it's a in the range of 2 to 10 x range. So or 5 of magnitude actually. So yeah, these are the challenges and solutions. So as I said, because it's a theoretical framework, it's not practically possible right now. But in the future, what can say as I said before, the lot can be a lot of lot can be. So it can be like maybe in a couple decades. So yeah, the challenges, the major challenges are like storing the information, like the each atomic information of like the atoms are sliced and the quantum information of that atom is stored. So if you say a human body, there are trillions and billions of atoms are there. So storing each atom's quantum information is like we need more than one universe is required for storing that much of data. So storing is one of the issue. So yeah, and maintaining the coherence, like the system can be very sensitive, as mentioned before. That's why we say that quantum mechanics can be counterintuitive and fascinating, as the Feynman said. If Feynman also said that he doesn't understand quantum mechanics because it's very bizarre, it can be very strange. Also, Bell streaks and EPR paradoxes are similar to that quote of Lord Kelvin. Um, yeah, these are the summary of my presentation for theoretical framework, computational validation, quantum advantage. Yeah, thank you.
Well, not to be honest,
What we mean by Yeah, actually, when we see as a actually, I have show you some stimulation. So this is the diagrammatic state that the simulation produced. So yeah, this is the vacuum state. This is the fog state one.
What are you plotting? What are on the axes you're plotting? What? On the axes, you're plotting something, right? Taking diagrams.
Yeah, it's actually the Wigner function plotting.
You're plotting the Wigner function.
Yeah,
And what are on the axes? Is there some intensity on one side? You're putting some numbers.
it's not clear.
What is it?
Yeah, the axis space is the Wigner function they use, the efficiency and the depth negativity, the negativity and Wigner negativity positivity, and like it can be like when you say planar space, the negative probability means that the probability can graph its emergence. The emergence will be in the depth step. So we'll be measuring that too. Sorry,
That's the color.
yeah.
That's what is on the X and Y axis here. Is it the physical, what physical constitutes?
So I'm not sure of it. Check it. Sure.
You make the switches or these are
No, it's such a SMT.
so you can calculate.
Yeah, for states. Yeah. When you say graphically, when we represent this, so I saw it's a higher topic. I'm not sure I'm actually correct, but I will try to explain it. So coherent states are like when we graphically represent it, it will be a kind of a circle, and squeeze state will be kind of an elliptical shape. So using the elliptical, like when the graphing say the elliptical, where the two coherence of this is squeezed, and it enables the classify the non-partiality, and it can be used for knowing the radiation, like knowing the interaction field measurements and taking the images too. So like it's depending on the Wigner's space. Yeah, Wigner's function. Yes, Wigner proximity to Wigner's function. Like maybe for already a long time. Yeah, negative voltage and non-classical. Actually, Wigner functions can be positive and negative. When it is negative, it's known as the non-classicality existence. Proves the non-classical existence. Actually, it's actually Bell states actually when Einstein, Kautsky, and Rosen introduced EPI paradox. So he mentions that God doesn't play direction universe. So Bell came up with his theory like testing is it right or wrong? Einstein was so influential at that time. So he suggested one experiment, and the experiment was conducted by Aspect, and like concluded that the like quantum mechanics is proven to be right other than the classical physics. So yeah, from that we also know that the no cloning theorem, no unknown quantum states can have similar copies of the quantum information. What is non-classical? In novel quantum guys, we are going to we are going also topic, but that was one. Yeah, actually, do you have my paper? I can also send the paper. In the paper, I have
Go.
the paper. Yeah. Actually, in the paper, I also mentioned about sorry, but it's a in our point in that how you can say that the issue, yeah. Okay, yeah. Say and as you should know in the one you might be using Wigner functions or other probability solutions. Wigner functions using there are two kinds of negative positivity, like Wigner positivity and Wigner negativity. Both are used for your integrating. Both are used for implying the uh, what we say like the non-classicality of states of time. Yeah, thank you.
With this, we'd like to bring the first day to a close. A big thank you to all participants for their wonderful presentations today and to our judges for their time and insight. We look forward to seeing you day after.